Hello, everybody, and welcome back to Mathematical Statistics on this fine Friday right before a break. Yeah, 4B is a weird one. It says to prove that for the given problem that there's no unbiased estimator for the given thing whose variance achieves the Crumier-Rao lower bound. So in problem 4, you have, oh, by the way, you might have heard from the other class because the other instructor is good at getting these notifications out and I'm not. 3A, it says find the UMVU for tau of P, but doesn't tell you what tau of P is. It should just be P. But 4B, we have X1 through Xn IID Poisson with parameter lambda. And you are looking at the function tau of lambda, which is the probability that any one of these is 0. And if you go to the Poisson distribution, that's e to the minus lambda, lambda to the 0 over 0 factorial. So e to the minus lambda. So there's your function of lambda. And part A, you want the UMVU for that, uniformly minimum variance unbiased estimator. And this consists of 2 steps by the Lehmann-Scheffé theorem. Step 1, you want to find a complete and sufficient statistic. And step 2, you want to find a function of that statistic that is unbiased for this. This one is tricky, but I think we've already done it. So this is an example of really Rao-Blackwellization, but I think you can get away with, like, you can find it in your homework or solutions because the indicator that x1 equals 0 is an unbiased estimator for this tau of lambda, but that is not the UMVU. But if you use the Rao-Blackwell theorem and condition on a complete and sufficient statistic, then you will have another unbiased estimator that is a function of the complete and sufficient statistic. And that is how you find an UMVU. So if this is complete and sufficient, then the answer is the UMVU. So this is what you would have to do in the case where you couldn't guess a function of the complete and sufficient statistic whose expected value is this. But I am totally digressing because I wasn't even asked about A, I was asked about B. And B sounds scary because it says to prove in this problem there is no unbiased estimator for tau of lambda whose variance achieves the Crumier-Rao lower bound for tau of lambda. So I would, part 1 of B, I would find the variance of the estimator, where this is the estimator from part A, or specifically the UMVU from part A. And then the second part, still in part B, I would find the Crumier-Rao lower bound for the variance of all unbiased estimators. And you'll see that, or you should see that your variance of your UMVU is actually strictly larger than the Crumier-Rao lower bound. And that tells you, I mean, you can't go any lower than the UMVU. So that tells you there's no unbiased estimator whose variance will achieve the Crumier-Rao lower bound. So it sounds scary, like it's a proof or something, but it's there is no unbiased estimator achieving the Crumier-Rao lower bound. You can figure that out if your UMVU does not achieve the Crumier-Rao lower bound. Yeah, 5, we already did in class. So I am gonna point you to, I'm just gonna get you started and point you to, I'm up to I have one video missing and I believe this is in that last video. So I'll get that posted today. So in the lecture for this Wednesday, sorry, I'm having all sorts of issues today. I can't see out of one eye at all. And I took a medication again that gives me vocal tremors. So sorry. I was trying to put a number here. It was Wednesday's lecture. So step 1 is to find a complete and sufficient statistic. And that you can definitely grab from class because completeness here is hard. So for the uniform zero theta distribution, we showed in class, and you can just say that the maximum is complete and sufficient. We got sufficiency from the factorization criterion, and then we showed completeness the long way. And you don't have to show that again. And so that is step one of finding an UMVU. And step two is to take its expectation and say, am I going to get theta? You're not going to get theta, but you're going to get some constants in front of theta so you can adjust it to turn it into an unbiased estimator. So your answer is going to be some constant in front of the maximum whose expected value gives you theta. Okay, so this is going to be our last lecture in this sort of sufficiency stuff. When you come back, we're going to talk about, oh, problem 2A. We're going to talk about generic hypothesis testing. But yeah, I got a question about 2A. So this is the Pareto distribution, and A is the much easier one. So we have X1 through Xn, IID Pareto with parameter gamma. And in part A, you want the UMVU for 1 over gamma. And that's actually the easy one, because once you find the complete and sufficient statistic, if you take the expectation, you're going to see something that is almost 1 over gamma, and that you can adjust. And the harder one is part B, where you're trying to find the UMVU for gamma. And I would start with the statistic and try flipping it over, much like we did when we tried to find the an unbiased estimator for lambda for the exponential distribution. So step one here is to write out the joint PDF and to look for that exponential family form factorization. And then to grab this as your complete and sufficient statistic, and you can say that is complete and sufficient by 1 parameter exponential family. And I think that's going to be pretty weird looking with logs. I haven't worked it out, but I'm pretty sure that you're going to see the sum of the logs of the 1 plus xi. You should check that. Don't take that blindly. Pretty sure that's going to be your complete and sufficient statistic. And this for the Pareto is something we have worked with a lot. If you want to find the expectation, you actually can do the integral. So the expected value of S is the expected value of that sum, and you can pull the sum out, and because they're IID, you would get n times the expected value of one of them. And I think the integral is actually not a bad substitution if you put this in front of the Pareto PDF and integrate. But we've been dealing with this instead by finding the distribution of this. And if you want to go ahead and say that you know this because we've written it, you may not know it, but we have done it a lot. This is exponential with rate gamma. We've seen that in class and on a couple of homeworks, so you could just say that. And so that gives you the mean is going to be 1 over gamma, because that is the mean of that exponential. So you just need to move the n to the other side to get 1 over gamma. So that one's nice. And then for part B, the UMVU for gamma, because the gamma was in the denominator, I would try flipping the sufficient statistic and using the same trick we always do. So this is the expectation of 1 over a sum of logs, and saying that the log is exponential. So this is the expectation of 1 over a gamma random variable, where this W is gamma with parameters n and lowercase gamma. Okay, so awesome. We had just started talking about minimal sufficiency. A minimal sufficient statistic is a statistic that is sufficient and can be written as a function of any other sufficient statistic. So the informal definition I gave you last time is that it's sufficient and down to the lowest dimension. I also gave you an example of why that's not exactly true using a single, a sample of size 1 from the normal distribution, but it will get you through this course. So if you think of a minimal sufficient statistic as minimal and lowest dimension, it's not exactly the definition, but again, it will work for anything you might be asked in here. The grads have a grad problem, which is pretty leading, and so hopefully not so bad because it takes you through the steps, but it is a theorem that I do want to mention for everyone, and that is if S is a statistic that is complete and sufficient, then it's minimal sufficient. So if you think of minimal sufficiency as this kind of lowest dimension thing, then that gives you some hints about looking for complete statistics, because if you write out, if you do not have an exponential family where it's easy to pop out a complete and sufficient statistic, so you're going back to the factorization criterion to at least find something sufficient, but you can factor it and factor it more and factor it more and keep reducing the dimensionality of your sufficient statistic. Like that is how I would start in trying to find a complete statistic as well, knowing now that if it's complete and sufficient, it's going to be minimal sufficient. So the lower dimensional stuff. In the uniform example, we had the statistic x1 through xn, and we had the statistic, the min and the max, and we had the max. And we can prove that this is minimal sufficient. I have a theorem for you that I was going to state today, but I'm going to spare you now, and I'm going to type it up for you, but you don't even have to read it. It's just for fun. It's a theorem about how to more easily identify minimal sufficient statistics, because it's really hard to guarantee that you've gotten as low as you can go. So, but this is an interesting theorem, which I think gives you some ideas when looking for a complete statistic, which is something you do need for an MVU. Okay, so that said, I would like to, in the time I have left, talk about something leading up to Basu's theorem. It looks like this. We're not ready for me to state it, but it is a theorem that will allow you to show that two things are independent in a very strange way, and you will probably not use this for years and years, and then one day, way in the future, it will come up and you'll just be like amazed, because you can show some things are independent that look really dependent in a really strange way without having to look at joint PDFs or anything. So to that end, I want to talk about something called an ancillary statistic. And these are statistics whose distribution does not depend on any unknown parameters. Now remember, statistics are not like pivotal quantities. They cannot have parameters in them, because some of you might be thinking right now of the normal distribution and n minus 1 times the sample variance over the true variance being chi-squared n minus 1, and this is unknown parameter free. But this doesn't count as a statistic because it has a parameter in it, but it would count if that parameter was fixed and known. So let me be just slightly more specific. An example of an ancillary statistic would be if you have x1 through xn, IID normal with mean mu and variance 1, then n minus 1 s squared over 1, which obviously you don't have to write, is chi-squared n minus 1. And so this is actually a statistic now. Again, a statistic can't have an unknown parameter in it, and its distribution is parameter free. So n minus 1 s squared is ancillary using this new definition of a statistic that doesn't depend on the parameter. And this seems like an opposite of sufficient statistics, because sufficient statistics contain all of the information about the parameter, and these contain none of the information about the parameter. And I was going to go through, I think I'll just state this, quick ways to find ancillary statistics. So one way to find an ancillary statistic is if you have what is known as a location parameter. So here are two kind of big classes of ancillary statistics. So number one is that your theta that you're working with is a so-called location parameter. And this means, I don't know why not being able to see or speak means I also can't write. This means that the PDF, doesn't have to be the joint PDF, is or can be written as some other function like F naught that doesn't depend on any parameters. And you plug in X minus theta naught. So here, F0x is theta free. This could be like for the normal mu1, that PDF looks like f of x and mu. It's going to look like 1 over the square root of 2 pi e to the minus 1/2 x minus mu squared. And this is f naught of x minus mu when f naught of x is 1 over the square root of 2 pi e to the minus 1/2 x squared. So that's a location parameter. So I'm still within this number one. If you have a location parameter, then any statistic that is location invariant, and I'm about to define that, is going to be ancillary. So the definition of location invariant, the statistic t, which is some t of x, is location invariant if the t function, and you can look at this capital or lowercase, but if t of x, which is t of x1 through xn, if this is equal to t of x1 plus some c out through xn plus some c for all c, for all real c. So the sample variance, it's just saying, if you shift the x's, it doesn't affect the value of the statistic. And an example, again, is the sample variance. The sum of the xi minus x bar squared over n minus 1. Because if you look at like yi defined as xi plus some c, then y bar is going to be x bar plus some c. And when you plug in the fact that xi is yi minus c and x bar is y bar minus c, if you plug those in up here, you can rewrite the sample variance in terms of the y's, and the c's are going to cancel when you have the minus c on both of these or the plus c on both of these, depending on whether you're starting with the x's or starting with the y's. Let me just say it this way, as I have been saying all along. If this is your data on a number line, it's a measure of spread about the sample mean. And if you move your data up or down, then the sample mean moves up and down and the spread does not change. So that's an ancillary statistic. Okay, so the second class is scale invariant or scale parameters and scale invariant statistics. Did I ever give the conclusion up here? Yes, location invariant statistics are ancillary if you're dealing with a location parameter. The scale parameter means that your PDF has the form 1 over theta, some f naught of x over theta. I actually call it a scale parameter if I see something like this, which is how many more of our PDFs are. But technically in the literature, if your PDF can be written like this, it's called an inverse scale parameter. And you can imagine like the exponential, right? If you have f of x and lambda is lambda e to the minus lambda x, that is f naught of lambda x times lambda, where f naught is the exponential rate 1. So in this notation, that lambda would be known as an inverse scale parameter. And then we have the concept of a scale invariant statistic. And we can conclude that they are going to be ancillary. And I was going to prove this today, but I am going to spare you. If you're working with a location parameter, then any statistic that is location invariant is ancillary. I was going to do a big Jacobian problem where I took my x's and I turned them into y's, and each y was an x plus a c, and I found the joint distribution of the y's, and it was theta free, and it was going to be great. But let me finish off what I'm trying to state in problem 2. So a scale invariant statistic, that is one where you have a statistic. It is like some function of the x's, and then the function of the little x's is equal to the function of the little x's multiplied through by a constant, as long as that constant is non-zero. And I claim that scale invariant statistics, when you have a scale parameter or an inverse scale parameter, they're ancillary. So scale parameter plus scale invariant statistic implies the statistic, that scale invariant statistic, is ancillary. I was going to spare you the proof of that one because you would have just seen the other proof of the location case. So why do I want to be able to find ancillary statistics easily? Because I have some exciting theorems that will allow us to show that some things are independent in a very, like in a whole new way. So the last thing I want to do is I have two things for you. First is that I'll call it a theorem. I don't usually write it as a theorem. I'll call this theorem 1. If S is sufficient and T is any statistic that is independent of S, then T is ancillary. This is not nearly as interesting as theorem 2, because theorem 2 is going to give us conditions. I want to do the converse of this. I want to say, if I have something sufficient and something ancillary, can I say they're independent? Because that would be a great way to establish that random variables are independent when you can't write out the joint PDF stuff. But I do have to put in one more condition for that to hold, and that's this really famous theorem called Basu's theorem. But sufficient statistics contain all the information about theta. Ancillary statistics contain none of the information about theta. They seem to be opposite in some sense, and this theorem 1 and theorem 2 are those two senses. So let's prove this theorem because it's super quick. If you have something sufficient and something independent of that sufficient statistic, the independent statistic must have a distribution whose parameter does not depend on theta. So number 1, by definition of sufficiency, if you look at the joint PDF of x1 through xn, given that s equals s, this is whatever it is, but this is going to be theta free. That was how we first defined sufficiency. And so if you condense the sample into a statistic that I'm going to call T, then that's not going to be able to pick up any information about theta, because the distribution of this statistic can be derived from the joint distribution up here. So the distribution of T given S, this is something you can get, like maybe these were IID Poissons and T was a sum, which is another Poisson. And if it's a sum of Poissons in this conditional land that does not depend on the parameter lambda, then it's not going to now depend on the parameter lambda. So this will still be theta free. You're actually losing information. So you're certainly not going to gain anything about theta. And so the final thing I want to put here, there's a little hand wavy, is that we have T is independent of S. And so that means that the conditional PDF for T given S is just the PDF for T. The given S does nothing. That is one way people define independence, through conditional probabilities or conditional PDFs. And so this implies that the PDF for T is equal to this guy, which we know is theta free. So if the PDF for T is theta free, this means that T is ancillary. That is the definition of ancillarity. Okay. I have one more thing to talk about, which is the cool thing. And maybe we'll stop early because I can't see anything. And we're on vacation soon. Okay, so the second theorem is, I would love for this to go the other way. What is the other way? I would love to be able to say, if I had a sufficient statistic and an ancillary statistic, that they must be independent, because independence is so important for so many calculations in statistics and can be hard to show. Ancillarity may be less hard to show, especially if you fall into one of those categories of location or scale parameters. But I can't quite give you the converse of this theorem. What I can give you is a really famous theorem known as Basu's theorem. And it says that if S is complete, so we have to throw completeness in for this to work, and sufficient, if T is another statistic that is ancillary, then S and T are independent. So to get this kind of converse of the previous theorem, I did need to add in completeness. And so let's prove this because it's really easy and kind of cool. And this is something that is going to come into the back of your head like 30 years from now, where you're going to be trying to show something's complete and you've tried everything, and then you remember Basu's theorem. So you're welcome. Okay, so let's prove it. So I'm going to start off by considering the following function of the random variable S. So consider the PDF for T minus the conditional PDF for T given S, evaluated at T given capital S. So there's some T's in here, but this is random, and as a random variable, it's a random function of S. You know, for a fixed T, think of S as the random variable, and this is a new random variable. Okay, so next I want to look at the expected value here. If I take the expected value of this function, There's only one random thing here, and that's this S over here. So the expected value is going to be with respect to S and the PDF for S. So this is an expectation with respect to the PDF for S, because that's the only random thing. So when I take this expectation, the first part just sits there because it's constant with respect to S. And then the second part is going to be the integral of this function. So this is now like a g of S, and you make it lowercase and put it in front of the PDF for S. So this is the conditional PDF t given little s times the PDF for little s for S. This is, again, like some G of S, and I'm using the law of the unconscious statistician to take like G of little s in front of the PDF for S. So if I multiply this conditional PDF times this marginal PDF, that gets me the joint PDF. And now I'm going to integrate out S. So this is ft of t minus the integral of ft comma s t comma s ds. And these integrals are all over the entire space, minus infinity to infinity. So this is this guy minus the marginal, and we get 0. So I started with a complete and sufficient statistic S, and I have a function of that complete and sufficient statistic whose expected value is 0. So by completeness, I know that the function inside this expectation is going to be 0 with probability 1. So S complete implies that the function that we just took the expectation of with the random S is 0 with probability 1. And so this tells me that f of t given s is equal to ft of t. And I've got some probability 1 and probability 0 statements that I really should make here. But this means that the conditional PDF with a little s for all little s's that the big S can possibly take on, that S could be, is equal to this. And this is one way to show independence of T and S. The conditional distribution is just the marginal of the first guy. So T is independent of S. Okay, so I should give you an example of how this will work. I am going to hold off on that and just call it a day and wish you all a wonderful vacation week. I will still be checking my email if you have any questions about the homework or anything else. And I am going to type up that theorem about minimal sufficiency that you don't have to read. But thank you for sticking around and being here in the first place today.